that we measured and the NRE position of them, as we assign comparing with the theoretical structure of these bands. As you can see, for this position, energetical position of the bands, the gap that we get is 0.85, that is bullseyeing the predictions for the GW model. But also we got a state in the middle of these two states that was not predicted for the infinite graphene nanoribbon calculations that we did. Instead, if you repeat these calculations for a finite graphene nanoribbon, you really get this state. So this is a hint that this state is an n-related state, or an n state, as we normally call it to make it faster. And if you repeat these calculations, having spin sensitivity, you see how this state can be divided into states that are singly occupied by one electron. So these are the radicals that we were expecting to see. Here is a comparison between the theoretical and experimental data, and you can see how they match almost one-to-one. So we think we are going in the right way here, or we thought that we were doing. And also you can see here another interesting comparison. That's the comparison between an infinite graphene nanoribbon that you put in the number of unit cells that you are trying to plot. So you are not taking into account the edge effects, and repeating these calculations, taking into account the edge effects. And you can see how there is an extra state that appears in the middle. That's this edge state that we were talking about. So it is really an effect of the borders. It's interesting to see how the edge states, or these end states, open a gap as the ribbon grows closer. To study this thing, I'm going to show you the case of the 12 unit cell graphene nanoribbon. This is the case, you can see it here. And if we take a line scan along the edge of this graphene nanoribbon, you can see how when we plot the stack of all the ADV spectra of the ribbon in energy from 2 electron volts to -2 electron volts, we can see the structure of the conduction band, the structure of the valence band, and also the band gap that we were predicting before. Here's a little bit bigger because the ribbon is confined in the X direction as well. So the gap is bigger than 0.85. That was the case for the quasi-infinite graphene nanoribbon. And in the middle, you can see the end states that we were talking before that are not independent anymore, are not two states independent on each side, but they are forming a bonding-antibonding couple. You can see how the predictions, how the theoretical studies predicted this behavior before. And when studying this behavior with the line, you can see here line scans taken for different lengths of graphene nanoribbons. And you can see how these independent end states that are here close to the Fermi level and are singly occupied, or will be if the goal wasn't there. As the ribbon grows shorter, they start hybridizing together to form a couple bonding-antibonding that's not singly occupied anymore, but forming a doubly occupied state and a non-occupied state on the top of them. Trying to reduce the effect of the gold on these graphene nanoribbons, what we did was moving this graphene nanoribbon by atomic manipulation using the tip over a monoglayer of sodium chloride. As you can see here, just from decoupling it with the survey that we took, the aspect of a ribbon already changed a lot. So we see that it's really affecting, the decoupling is really affecting the graphene nanoribbon. Here we can see a comparison between the band structure of the graphene nanoribbon over the gold at the left and the graphene nanoribbon decoupled by a monolayer of sodium chloride at the right. We can see how decoupling already increased the band gap because the conjugation with the gold was reducing the band gap of these graphene nanoribbons. And we can still see these end states in the middle of the band gap that when were decoupled, that the decoupling of the sodium chloride wasn't enough for moving the Fermi level back to its original position, because these states were supposed to be half-filled in theory. Here is a comparison between the resolution that you can get in these graphene nanoribbons over the gold 111 over a monolayer of sodium chloride, and the comparison with the simulated images. We can see how the resolution already improved a lot just by putting a monolayer of sodium chloride in the middle. Here is a detailed study of the bands of the graphene nanoribbons as the ribbons grow longer. We can see how for all of these studies, for all these ribbons, the end states are over the Fermi level because the gold is taking out these electrons from these singly occupied states So even for the sodium chloride graphene nanoribbons that we expected to be decoupled from the gold, they still are empty. So we cannot observe this Kondo feature that you expect for a magnetic state because the state is empty, even when it's over a sodium chloride layer. So as we couldn't demonstrate like that the magnetism of the graphene nanoribbon, we went for transport measurements on these graphene nanoribbons, looking to measure the conductivity of them and so. And also maybe just by lifting these graphene nanoribbons from the surface, maybe we could reduce the effect of the gold and shift back these end states back to the field area or under the Fermi level so we can observe this Kondo effect. Here we can see the technique that we used for doing these measurements. We put the ribbon half on the sodium chloride and then approach it with the tip in the tunneling regime until we saw a jump in the current that was the contact between the tip and the graphene nanoribbon. And as you go back to the original position, you see how the slope of the curve is not as slopey as it was before, because you are not anymore in the tunneling regime, but you are conducing across the graphene nanoribbon. And we can see how this small slope gives us a hint about the conductivity of these graphene nanoribbons, that is one of the best that has been ever measured on a material. And we repeated these experiments while doing DIDB ramps between voltages, between 100 millivolts and minus 100 millivolts. So we get into contact, start ramping, and start lifting the graphene nanoribbon. You can see it here. This is the bias, and this is as we lifted. And we can see how, as we lifted the end state, that's this bright spot here, shifted towards the Fermi level as the gold started affecting less and less the Fermi level of the graphene nanoribbon, until eventually the end state got under the Fermi level and got filled again with that single electron that we were expecting it to have when it was freestanding. As it crosses the Fermi level, we can see how this Kondo feature appears on the zero. That's the main footprint to indicate that you have a magnetic state on your graphene nanoribbon. It's interesting to say that this Kondo feature doesn't appear on the empty orbital regime, and we consider this a proof that what we are having here is a Kondo feature in this case. But something that we also wanted to know is that if we were seeing the Kondo coupling between the ribbon and the tip, or the Kondo coupling between the ribbon and the surface of gold that was beneath the sodium chloride. So for checking this, what we did was oxidizing these graphene nanoribbons by exposing to oxygen for 10 to the minus 5 millibars of oxygen for 1 hour. And we got it. We got these graphene nanoribbons that are oxidized on the end, where the end state would be placed, and it's forming maybe a ketone group here. And we see how when taking this line scan along the edge of the ribbon, the end states are not present anymore on it. You can see they will be here. But this is not the case that interested us. We were looking for a graphene nanoribbon with a singly oxidized side, and that's what we got. You can see here how in this graphene nanoribbon that you can see here, there is one end state and the other one has disappeared because of the oxidation of the graphene nanoribbon. So what we did was repeating the transport experiments on these graphene nanoribbons over an island of sodium chloride and lifted from the pristine side. That's this one that you can see that is brighter. As we lift from this side, we see again the shifting of the end state of the graphene nanoribbon that we saw before. And when lifting from the oxidized end state, we just see a decrease in the current that can be related with the semiconducting nature of these graphene nanoribbons, but we don't see a shifting of the end state. So this gives us a hint that what we are watching is the coupling between the tip and the graphene nanoribbon. Repeating this experiment for a longer graphene nanoribbon, we keep going after lifting a little bit because for the previous ribbon, the ribbon fell and we couldn't measure the Kondo effect. And for this one, we saw how as the end state crossed the Fermi level, the Kondo feature appeared in the middle, indicating that we were measuring the coupling between the tip and the ribbon. When repeating this experiment from the other end, we saw nothing. So this is a unequivocally proof that we are measuring that coupling. So to finish with this talk, I'm going to do a summary. So I can say that we assigned the band gap of these ribbons on gold to 0.85 electron volts. We can also say that we identified the presence of these topological end states on the 5 graphene nanoribbons. We can say that we studied the evolution of these graphene nanoribbons with the length of the ribbon and their hybridization. And to finish, we performed some transport measurements on the graphene nanoribbons and proved their magnetic nature. Thank you for attending this talk, and I'm here for your questions.
Okay, thank you very much, Alejandro.
I'm on time?
Very interesting, kind of.
Oh. Okay.
Many interesting results, and we already have a question, a couple of them actually. First one by Jorge Lobocheca. The question is, how probable is to change the edge of the chain when you manipulate it? I guess it can dramatically affect the edge states.
Well, when manipulating, it wasn't that common, as we were, when we did the manipulation, we were applying voltages of like 2 milli-electron volts, because the current increased a lot and our system cannot measure so high currents. So we didn't see really modifications on the end state while lifting. We saw it when, for example, applying a ramp, but that was going over 2 electron volts. Something that really happened once was that the ribbon fall, and as it fall, it like bent and broke, but it's not that common to break the graphene nanoribbon just by lifting it. Something that we did observe once was the reaction in the end just by applying this ramp while lifting, but it's not that common. And of course, if you modify the end, you will probably see a change in the topological regime of the graphene nanoribbon. Also, if you modify it by other ways, probably.
Okay, and we have another question by Bruno, whose last name I unfortunately do not know. So he says, very nice. I have a couple of questions regarding the conductance measurements. Did you check the structure of the edge ribbon after the measurement? Did you try to measure resonance transport through valence and conductance bands?
We weren't, well, the structure of the graphene nanoribbon, we checked it by bone resolution before and after the transport measurements. What we saw was the normal structure that we were expecting, and as we know, a different group on the end of the ribbon will look different in the bone resolution structure, so we are pretty sure that what we are having is a pristine graphene nanoribbon that has this pi orbital, that's not a sigma orbital. And what was the second question, sorry?
Did you try to measure resonant transport, I guess, through valence and conduction bands?
Oh, okay. Well, one problem that we had on this system was that we cannot measure really high currents because our system doesn't allow going higher than 100 nanoamps. So what we did was measure just in the band gap. So we couldn't measure in the conduction and valence band. We saw the conduction and valence bands because, of course, we tried to go the farther we can in voltage, and we saw this sudden increase of the current that is the conduction and valence band, but we couldn't perform measures across them. We saw something like a hint of, as we lifted, the valence and conduction bands also shifted a little, but we don't have strong enough results to talk about that right now.
Okay, we are running late, but I will allow 2 questions. Please be quick. Ferrer says, many thanks for your talk. I would expect that the energy of the edge state be way larger because of Coulomb effects, as the edge state is much more localized. It's much more localized than the ribbon edge state. Could you explain why this is not so?
Can you repeat, please? Sorry.
A little bit. I would expect that the energy of the edge state be way larger because of Coulomb effects, as the edge state is much more localized than the ribbon edge states. So the end and the edge. Could you explain why this is not so?
So why the different? I haven't got it, sorry, still.
So the comparison between the edge states, the long one, and the edge at the edge of the ribbons and the end states. So what he's saying is that the Coulomb effects would be way larger.
Well, these graphene nanoribbons don't have an edge state in theory. What we are seeing is the localization of the bands on the ends, on the edges, because we can see them better there, but that's not an edge state as I understand. Maybe I'm not getting the question, sorry.
Okay, well, you can, maybe
Okay.
you can.
Yeah, maybe we can solve it
later and then think about it.
Okay.
And the last question by Manuela Garnica is nice talk. She's saying, a nice talk. Did you try with other tips? Do you expect different condo behavior?
Well, in theory, we may expect a coupling between the tip and the ribbon if we perform these lifting experiments with a different tip, maybe. One problem is that as you take the ribbon, most of the times you break your tip. Well, like maybe 10% of the experiments are successful, and the other 90% you break your tip. So it will be hard to get a good measure for your tip, then lift, then get the tip again. So I don't know if that can be a big impediment for performing these kind of measurements, but in principle, you will expect a different coupling for a different tip, of course.
Okay, so thank you very much, Alejandro, for the talk and the.
Thank you all.
But we are running late, so let's now change to the next talk. Also from the San Sebastian, a different San Sebastian team. Niklas, please, if you can share your presentation.
Yes. Okay.
Okay. Well, next contributed talk will be by Niklas Friedrich, who's coming from the Nacho Pascual's group at the Nanogune in San Sebastian, and he will be talking about boron-doped graphene nanoribbons. Okay, Niklas.
Yes. Thank you for the introduction. Hope everything's going fine. If something's not working, please let me know. And thank you also for giving me the opportunity to present my work here at this very interesting concept conference, which I think will be a good contribution to reducing the environmental impact science has. And this is something very nice to be part of. Yeah, today I'll present here our newest work on spin texture in graphene nanostructures. And graphene is very interesting material for such kind of experiments, because on one hand, by bottom-up synthesis, as we've seen in the talks before, we can think of designing arbitrary structures of spin, of having interaction between them. On the other hand, it's a very good conductor with very long spin coherence time. So this is very nice for applications like spintronics or quantum computing, and makes it therefore very interesting. So how do we actually get spin texture in graphene? And there are different ways to do so. For example, the shape. We've heard about the LEAP theorem, which leads to here triangulene being a spin 1 ground state, and therefore making it a extremely reactive molecule. And it was published 3 years ago in the group of Leo Gross. And then this year, we have a very similar molecule, the Clar goblet with a spin 0 ground state, where the magnetism was proven actually here by this inelastic spin excitation. Also in the first talk today, we had a very nice and lengthy introduction to the topology and SSH model in specific. And there are also these two very, very nice works of the group of Mike Cromie and Roman Fasel were mentioned, where they use essentially that different graphene nanoribbons have different topology. And then if you fuse them together at the interface, we get an edge state which hosts spin polarization. And in these two works very nicely, they use these topologically protected edge states or interface states to build an SSH chain, which is the toy model for topology. And just a short reminder, we heard it before, but in the essence of the SSH model is that you have coupled dimers with an intra-dimer hopping of T1 and an inter-dimer hopping of T2. And then depending on the ratio of these two values, you get a trivial, metallic, or non-trivial system. And now a third way to induce spin in graphene is by inducing heteroatoms. Here in this work of Stevie Louis of their group, they claimed that inducing boron atoms here at the center of 7 armchair graphene nanoribbons, and doing so periodically, what you get is a coupling of antiferromagnetically coupled spin polarized states here inside the graphene nanoribbon. But the experimental evidence for that was still lacking so far. So we took a look at what is this doing, the boron doping doing precisely. And what we find here is that the boron, it has 1 electron less than the carbon backbone. So it essentially, on one hand, breaks the conjugation here in the center of the graphene nanoribbon, where the electrons of the valence band could move along freely. And on the other hand, it leads to a stabilization of this class sextet, which has a few hundred milli-electron volt stability. So very, very stable chemical group that doesn't want to break easily on both ends. So in a topologically trivial graphene nanoribbon, one would have it on one side, and then on the other side, you could still pass electrons of the valence band freely. While here on the boron doping side, you actually stabilize it on both sides. So this effectively breaks the conjugation of the valence band, and therefore it looks like the end of the graphene nanoribbon to the electrons in the valence band, and we have here spin polarized states showing up. And actually very interesting, if we do the DFT calculation, what happens is that the ferromagnetic alignment, as we can see here in the projected density of states on each side of the diboron unit, is 16 milli-electron volt lower than the antiferromagnetic alignment. And we can also rationalize this with a easy toy model by considering the two most important interactions. On one hand, the hopping, which, as I explained before, is very low, while on the other hand, the wave functions still have some overlap, and therefore Hund's rules apply, and we come up with a ferromagnetic coupling between the end states. Now, to synthesize these graphene nanoribbons, we took these two precursor molecules, deposited them on gold 111, went through the steps of Ullmann coupling and cyclodehydrogenation, and then we have these nice graphene nanoribbons with some depression along the carbon backbone. And this is really the interaction of the boron unit with the substrate, as we can see here in the CO resolved constant height image. We lose here the contrast, and therefore we can clearly identify where the diboron unit is sitting. But unfortunately, there was no magnetic signal whatsoever on the substrate. So we did the same approach as the group of DMARS before, that we started to lift the graphene nanoribbon. And what happens is when we approach with the tip of our STM here to one termination of the graphene nanoribbon, we have a increasing current. At some point, we have a jump to contact. And then upon retraction, we see a hysteresis. And also here this exponentially decaying co-tunneling current. Here in orange, this is the curve for a pristine graphene nanoribbon, which has no diboron doping. But for the boron doped one, we see something very curious. At a certain point, there's an increase in the current with a peak at ZP, and then it decays back to the exponential behavior that we see before. And we can repeat this experiment many times. We can go up, go down at different voltages, and the ZP will always be at the very same position. However, if we go to a different graphene nanoribbon with a different separation here between tip and diboron unit, then this ZP will also change. So there we see the very strong correlation. And to understand what is physically going on there, what we did is we took a DIDV spectrum at the position of ZP. And we see here a very nice and sharp or large Kondo resonance with a Fano line shape of half width at half maximum of 6 millivolts, precisely at the position of this highest current or locally highest current. And now in order to see if this is really the cause of this increased current, what we did is we took a whole stack of the DIDV spectra, and here we have plotted the bias against the tip retraction, corresponds to this gray area here, and in color, this logarithmic conductance, differential conductance. And what we see coming here from low retraction is we have relatively high conductance, but then within the fraction of an angstrom at exactly this ZP, the Kondo resonance really pops up. And then we can see that it is still present for another about 2 angstrom, although it even gets more narrow. Its line width gets smaller, and then here at 2.9 nanometers, it disappears. This is also very reproducible. We can actually go here exactly to that position ZP and jump forward and backward just the fraction of an angstrom, and the Kondo resonance will show up or disappear. And as we heard before, the Kondo is usually associated to a spin polarized state. So in order to understand what's going on there, what we did is we performed DFT calculations of really that lifted system. So not a toy model, but really as close as we can get to the real system. Extremely expensive calculations with more than 7,000 orbitals. We used Siesta to do so. And what we did is we took a look at the spin polarization present. And now we can compare here these 2 regions around the individual boron atoms of the diboron side. The boron atoms are located here at the arrows. And if they are both in contact with the substrate, the spin polarization is completely quenched. Here for comparison, the one of the free gas phase ribbon, and in solid, the system calculated here. However, the moment that we detach the first boron atom from the substrate, what we see is that in actually this region, the spin polarization re-emerges, and we can also see it here in the projected density of states. We have here a system with spin 1/2. Now, if we continue to retract the graphene nanoribbon, what actually happens is that we more or less restore the spin polarization of the freestanding graphene nanoribbon, and we have the spin equal 1 restored. What we believe is the most likely scenario that we measure in experiment, however, is here, because it matches very nicely with the experimental findings that the Kondo resonance appears that extremely sharply upon detaching the boron atom, and then decays in intensity, but is only present for a very short time. And then the quenching of the Kondo resonance corresponds to the second boron atom being detached from the substrate. And the distance of 2 angstrom corresponds reasonably well to a possible distance between the separation from the substrate of the 2 diboron units. Now that's very nice. We have here experimental evidence for for the magnetic state of 1 diboron unit. But what happens actually if we put them to interact? And the paper of the Louis group, they claimed that they should interact antiferromagnetically, actually with the spin polarization localized away from the diboron units, and here in the inside, not. And our DFT calculations confirm this, and we can actually understand this again using the SSH model by considering each diboron unit here as one of these dimers. Now, if we introduce a second diboron unit, we add to the intra-unit cell hopping the inter-unit cell hopping, and then we can take a look at the DFT calculated band structures and fit the band structure of the SSH model to this and extract the hopping parameters T-inter and T-intra. And this approach seems to be justified because what we see here is that on one hand, if we move the diboron units closer to each other, the hopping between the diboron units increases, while the hopping across one unit cell, here the T-intra, stays reasonably constant. And doing so, what we find actually is that here for this case that's shown here, we are very deep in the topologically trivial regime, and the graphene nanoribbon that's pristine actually is topologically non-trivial. So this explains why we see here the edge state. But now what's happening in the middle is we still have these two spins. However, here they have such strong kinetic exchange actually because there's nothing that's breaking the conjugation here in between, that they actually prefer to be in a closed shell state, and this quenches the magnetism in between. If we go to such a system experimentally, now we have here two diboron units located as close as possible with respect to each other with the available precursors we have, which corresponds exactly to the system that I've shown you before. And if we lift these graphene nanoribbons, we actually see here two peaks in the current upon retraction. And if we now map the DIDV across this region, we actually have to normalize the system because we are dropping here 3-4 orders of magnitude in current and therefore also in conductance. So in order to see something in this image, we need to normalize the DIDV spectra. But what we can clearly see is that we have here one Kondo resonance and here a second Kondo resonance that are separated by approximately 1.2 nanometers, which is the distance between these two diboron units, and matching pretty nicely. We can also maybe very faintly, but see a little bit that the first Kondo resonance seems to be quenched rather abruptly, while the second one here extends more or less into the limit of resolution of our measurements. So this hints to the state really expanding one time in the direction away from the substrate, while in the other time towards the substrate. And now a last very interesting case is here these now topologically trivial graphene nanoribbon made up out of only borylated precursor units. And in this case, the theory doesn't predict any spin polarization whatsoever. However, if we lift it, it's very interesting that we have here in the beginning nothing, then at some point we see a Kondo resonance appearing that disappears again, and then we have another Kondo resonance appearing that disappears. The separation between these two Kondo resonances is actually about 1.2 nanometers again. So it seems to be the case that we again have spin polarization associated with the diboron units. And doing a DFT toy model, we can actually explain where this is coming from. So for the precise moment where the boron atom here is still attached to the substrate, a spin polarization forms here at the last diboron unit of the freestanding part of the graphene nanoribbon. And we can reproduce here this spin polarization, which seems to be the case that we measure them here experimentally. So this is very exciting work. We are still in the process of figuring out what's precisely going on, but we wanted to share this already. So with that, let me sum up the main findings of the talk. I showed you that we can induce here a diboron unit in a graphene nanoribbon that induces a spin texture inside the graphene nanoribbon. We can probe it experimentally by transport experiments where we see a Kondo resonance appearing when we detach the boron unit from the substrate, which actually restores the spin. And we can also have these two units, or several of these units interacting with each other, changing the spin texture, and this reflects also in the experiment. And with that, I would like to thank the people involved in this work. We had here at Nanogune the STM experiments, at DIPC the theoretical calculations were performed, and in Santiago and Japan the molecules were synthesized. And of course, I would like to thank I'm looking forward to the questions.
Thank you very much, Niklas, for your very nice talk. Is there any question from the audience? Well, I have a small, well, it's not a question, but maybe a remark, I don't know, because for this last part that you have shown, the unpublished part, if you have a fully periodic doped ribbon, now the Kondo effect may come from both the tip or the surface, right? Because you have this, or you quench the one at the edge that you pick up.
The one at the edge is most likely quenched. As we can see here in the calculation, basically having only an anthracene unit here and not the double anthracene is not sufficient space to form a spin polarized state.
Okay, so it has to come from the surface.
Yeah.
Okay, and then we have a question from Jorge Lobo. He's asking how controllable is to construct the diboron units. I mean, do you have a recipe to form them with a certain control?
No, it's statistics. Of course, we haven't tried too much to do it controllably. What one could think of, for example, is by first depositing only the borylated precursor, annealing for a very short time in order to form very small nanoribbons and not do the cyclodehydrogenation, so that they still are radical, and then depositing the pristine precursors and go through the rest of the preparation steps. One could think of possible recipes like this. However, we haven't tried too hard to do it because just by statistics you find them on the substrate.
Okay, and one very last question because we are really 10 minutes behind the schedule. It's a question from Bruno de la Torre, and he's asking, did you see bond distortion from your high resolution images around the boron site?
Well, it's extremely difficult to say something there because the boron units actually are already bent towards the surface, so we are losing the constant height planar structure, and to disentangle there what effect comes from bond distortion in the sense of different electronic bonding and what effect comes from the height is I would say too much to try to get from that images.
Okay, so thank you very much, Niklas, and let's move on to the next question.
Thanks.
Jan Phillips, thank you. Gracias. Jan Phillips, who's coming
Hello.
from Santiago de Compostela. If you can please share your screen or your
Yeah. Can you see it?
Yeah, perfect.
Yep. Okay. Well, hello everybody. I'm Jan Phillips, as I've been introduced, and I would like to first of all thank you all for attending my talk and thank also the funding sources, and last but not least, my colleague Adolfo Otero Fumega and my PhD supervisor Victor Pardo for their enormous work making this paper possible and allowing me to be a part of it. And my talk consists of control 2D ferromagnetism in the 1T chromium telluride, and will be centering on the role of charge density wave and strain. So I just wanted to make a sort of quick summary of what we'll be seeing in this talk. And basically, we'll see the electron localization of d electrons in the d orbitals of the chromium telluride produce an out-of-plane orientation of the magnetic moments in the chromium atoms, and this will circumvent the restrictions imposed by the Mohn-Wagner theorem, which will allow us to have long-range ferromagnetism. Okay, so this is very interesting, and we'll also see that how a charge density wave appears and how this and tensile strain will enhance the localization and thus becoming mechanisms to control the two-dimensional ferromagnetism order of chromium telluride. Okay, having said that, I'm sort of going to make a very small introduction. I'm going to talk about our results on the bulk structure. I'll continue with the structural characterization of the monolayer, and I'll end up on the talking about ferromagnetism in the 2D limit. So I just wanted to put everybody in context. These are DFT calculation results, which have been done with a GA exchange correlation term using BN2K. Okay, so a little bit more of context. I just wanted to refresh the Mermin-Wagner theorem so we all know what we're talking about. And it basically forbids long-range ferromagnetic order in the two-dimensional limits, but we can actually overcome this by lowering the symmetry of our system. In our specific case, we did this through an external field, which will be tensile strain. It can also be done through a strong magnetic anisotropy, or with the appearance of a charge density wave phase. Okay, so what does our structure look like? Okay, well, this is our structure where the blue atoms are the chromium atoms and the gold atoms are the tellurium atoms. And we worked with the unit cell that's just appeared on the screen. And why did we choose it? Well, it belongs to the transition metal decalcogenide family, and which is an ideal platform for two-dimensional ferromagnetic studies. Mainly because the layers are bonded via van der Waals interactions, which make them very easily exfoliated, but also because the transition metal in the compound provides the d electrons, which contribute to the non-zero magnetic moment, which will be interesting as we'll see further on. Specifically, chromium telluride crystallizes in a 1T phase and has a bulk Curie temperature of 310 kelvins, which is approximately room temperature, and which makes it of great interest. So, going on to the bulk structure, this is the structure I presented previously. We can see lattice parameter A indicated here, which I'll probably refer to as in plane from now on, and we have the out of plane lattice parameter C. Okay, what we did is we calculated the magnetic anisotropy energy, which is basically the difference between the energy of our system when the magnetic moments of the chromium atoms are pointing in plane, minus the energy of our system when the magnetic moments are pointing out of plane. Okay, so in our convention, when this energy is positive, our magnetic moments are pointing out of plane. This creates a strong magnetic anisotropy, which lowers the system symmetry, which will allow us, when we get to the two-dimensional case, to circumvent the Mermin-Wagner restrictions. Our results in the bulk structure, the ones that have just come up on screen, where we modified the parameter C, the lattice parameter C, and for each of these modifications, we calculated the magnetic anisotropy energy. That computed one curve, and the rest of the curves was done repeating the same process for different values of the in-plane lattice parameter. So, what do we see in this graph? Basically, we center in the left region when we decrease the C parameter. What we get is the magnetic moments are pointing out of plane. But more interestingly, when we go to the right region, this is when we increase C and we're getting close to the 2D limit. The magnetic moments also point out of plane, but only when it's accompanied by an increase in the in-plane lattice parameter as well. Okay, so this is the sort of main picture that we get from the bulk structure, which will help us towards understanding the monolayer. So, when we go on to the monolayer, we characterized it. We started with this unit cell, which we call the normal state. And based on previous studies that report the charge density wave appears in some of the transition metal decalcogenides at the 2D limit, we wanted to analyze if it also appeared in chromium telluride. And to do so, what we did is we performed phonon band structures calculations, where the first thing we see is we have negative frequencies. Okay, this means that there is unstable mode. So this structure is dynamically unstable, and this is an indication of the existence of a charge density wave, but it's not a proof. Okay, so we needed to find a new structure that might be stable, and which is the one I present on the screen now. The atomic distances were reconstructed in such a way that, for example, now chromium atoms have only got 2 nearest neighbor chromium atoms instead of 6 like before. So that's what I'm indicating with the red triangles. And when we perform the phonon band structure for this new charge density wave structure, what we see is we no longer have the negative frequencies. This means that the instabilities are no longer present. So this charge density wave structure is feasible, but we don't know if it's our ground state yet. So what we did next was we computed the energy for the normal states and the charge density wave states for different lattice parameter, and we presented the difference as a function of parameter A in this graph. So when the difference is positive, the value of the difference is positive, what we have is our charge density wave is the most stable state, which is the area represented in red, while if the difference is negative, we'll have the normal state as the most stable structure, which is our area represented in blue. The first thing we see is that for any value of the lattice parameter A, the charge density wave is the most stable structure. So this, together with the phonon band structure, which we calculated previously, leads us to knowing that the ground state of our structure is indeed this charge density wave phase. Okay, but we also found something very interesting, which is we found an optical mode which actually drives the charge density wave to the normal state with a frequency of 1.96 terahertz, which will be interesting later to control the magnetism in our structure. So going on to the ferromagnetism in the two-dimensional limit, we've just seen that the charge density wave emerges at low temperatures. And now we go on to analyze the ferromagnetic order, starting with the electronic structure. Okay, so on the graph, what we can see is the density of states as a function of the energy, where the charge density wave are represented in red and the normal state in blue. And we're representing as positive values the majority spin channels, while the negative values in the graph represent the minority spin channel. So what do we read in this graph? Well, if we remember the image of our structure, we had an octahedral environment surrounding the telluriums were forming an octahedral environment surrounding the chromium atoms. But now that we've got a monolayer, this structure is trigonally distorted. So because of it, the d electrons are now distributed in two doublets and a singlet. And focusing on the highlighted orbitals, we know that for the majority spin channel, the singlet is fully occupied and there's two electrons in the doublet. So this leads us for 3 ball magnetons per chromium atom, a total magnetic moment, which translates as a valence of 3+ in chromium, which was confirmed in the calculations. But there's a high degree of hybridization with the p tellurium orbital, with the band, sorry, and this produces this metallic state, which we can observe. But we can also see in the density of states that it is typical that when the charge density wave phase appears, it opens gaps or pseudo gaps around the Fermi level, which is exactly what we're seeing here. But we can see this a bit better if if we go on to analyze the band structures. Okay, the band structure, what's been shown on screen is basically in both cases it's for the majority spin channel, for the band structure for the normal state and the band structure for the charge density wave. Okay, so because of the charge density wave atomic rearrangement, which I mentioned previously, bands are hybridizing, and we see the gaps which I mentioned a second ago, gaps and pseudo gaps open around the Fermi level. But this means that there's a depletion of states around the Fermi level, which lowers the energy of our system, which confirms again that the charge density wave is ground state. But we can see more things. If you remember the singlet I mentioned a second ago, it's highlighted in the band structures in pink. I'm going to surround it just so we know what we're looking at. And when we go onto the charge density wave, what happens is this orbital is much more localized, as we can see here. We can even see it better in the density of states. Okay, and this is one of the ingredients which I mentioned at the very beginning, which was fundamental to understand what we're talking about. And to continue our ferromagnetic study, we now computed the magnetic anisotropy energy for the monolayer as a function of the lattice parameter A. The first thing we see is that in the shaded area, for the experimental value in bulk, the charge density wave phase is very close to being feasible. The long-range ferromagnetic order is very close to being feasible. And it only needs a very small strain to actually send the magnetic moments out of plane. If we remember, out of plane magnetic moments are associated to, in our convention, to a positive value of this difference in energy. And this would circumvent the Mohn-Wagner theorem, which is very interesting because it means we'll have long-range ferromagnetic order. We can see as well that in normal state, it's also possible to send the magnetic moments to produce this magnetic anisotropy, but we need a much higher strain. But the message I want to send here is that we actually can obtain long-range ferromagnetic order. So I just want to sum up the main ideas of the talk. And in the bulk structure, we saw that decreasing the out-of-plane lattice parameter sent the magnetic moments out of plane, but increasing it, which means approaching the monolayer limit, also drove them out of plane, only if it was accompanied by an increase in the in-plane lattice parameter. Then when we did a detailed description of the monolayer, where we saw that the charge density wave is the ground state for any strain value, but we also saw that we identified an optical mode that connects both the charge density wave and the normal state, and this will act as a mechanism to switch between them and control the magnetism. And finally, we saw that charge density wave opens a gap around the Fermi level and localizes the d electrons. And we saw that tensile strain also has a similar effect, localizing the d electrons and driving the moment magnetic. Both of these situations drive the magnetic moments to point out of plane, and it means we've got long-range two-dimensional ferromagnetism. And this were the results we wanted to present to you. And thank you very much for your attention. I'll leave the reference for the archive, and basically this paper's been very recently accepted, so we're quite excited. And questions, please.
Okay, thank you very much, Jan Phillips, for a very clear and interesting talk, and also for being very much in time. So if there is any question from the audience, now is your chance. I have a question myself. Maybe I didn't get it right. When you describe what's going on in the bulk at the beginning of the talk.
Yeah.
Can you show the
Yeah, I'll go on to it. Here?
Yeah, exactly. So you say that when you increase the C parameter, which is basically going to the two-dimensional limit,
yeah,
this out-of-plane magnetization seems to be possible for different A values.
Yeah.
In a constant, but here what seems to happen for the experimental case is the parallel magnetization is the
yes, and it's actually in agreement with what we saw in the monolayer. If you remember, I showed in the monolayer that we need a little bit of strain to actually have in the charge density wave phase, to have the magnetic moments pointing out of plane for the experimental value of A. So what we need to do is it's two ingredients. We need in the monolayer, we need the charge density wave, and we also need a slight tensile strain. Okay. In order to have the magnetic moments pointing outwards, which is, monolayer and bulk case are slightly different, but the bulk just gave us an idea that we were going to need strain in the lattice parameter and the in-plane lattice parameter as well to get the magnetic moments out of plane. I don't know if I've answered your question.
Yeah, sure. So you need both. Right. You need the tensile, you need the tensile strain. Otherwise, and this is something that you can predict from the panel.
Yeah, these are all predictions, the DFT predictions, because the monolayer hasn't been actually synthesized yet. We as I said, transition metal dechalcogenides are promising materials. So if the next bit would be actually observing this experimentally.
Yeah, sure. Okay, thank you very much. We have a question from Jorge Lobo Checa, and he's asking for the charge density wave, how many unit cells are you considering for the 2D limit?
If you allow me, I'll just go to the slide. Okay, this is the unit cell for our charge density wave. Okay, what we did is we started. We had the normal state was our starting point. Okay, and we just computed we and the new structure based on that. But this would be our unit cell that we worked with. I don't know if that's answering the question.
I mean vertically, that's what he says.
Oh, vertically? No, just single layer. Yeah, so it's...
Yeah, so you did the calculations for the bulk, and then you kind of first simulated the limit of the 2D by...
yeah, to see where we could go.
Apart, but then these are truly 2D.
These are truly 2D, yes.
And he's further asking, if you go to 2 layers, do you lose the charge density wave?
Well, that's the next step we want to start analyzing, because we've started with a single layer, and the next bit will be few layer limit. So when I know, I can answer in further work.
So thank you very much. Thank you, Jorge, for your question, because this seems to be a like perfect way to finish this contributed talk. And so thank you very much, Jan. And
thank you.
now we'll be moving to the next talk by Sofía Parreira, coming also from the Nanoscience in Madrid. So Sofía, please go ahead and share your screen or your presentation. Okay, thank you very much. So Sofía, about how to tailor the magnetic anisotropy of lanthanides on surface-supported metal-organic frameworks. So Sofía, please. Thanks, and go ahead.
Good morning for everybody. So today I'll show some results on the magnetism of lanthanide metal-organic networks. The motivation for these works is related with the magnetism of single atoms, and the stabilization of the magnetism in single atoms represents the ultimate limit for the development of magnetic memories with the highest storage density. And some fundamental requirements for a single atom magnet are firstly a doubly degenerated ground state. So it's necessary to have 2 states where the magnetization can be turned between these states. And these states must be stable against fluctuations, and for this it's necessary a high magnetic anisotropy. And for practical applications, it's important to have long spin relaxation times, so the magnetization can be stabilized for large times. And lanthanides are promising candidates for this, since they have a strong spin-orbit coupling, which can lead to high anisotropies. And also the strong localization of 4F states reduces the hybridization with surface, increasing the spin lifetimes. Now here I show some results from the literature regarding the magnetism of lanthanide atoms. It has been demonstrated that it's possible to stabilize a magnetic remnants in holmium atoms adsorbed on a magnesium oxide surface with large spin lifetimes. And recently, it was also demonstrated by electron spin resonance that is possible to write and read magnetic atoms. So it confirms that it's possible to use lanthanide atoms to storage information. However, single standing atoms absorbed on surface, they can diffuse easily, and so they lack thermal stability and are not suitable for practical applications. And to overcome this problem, the next step is coordinated these atoms in network, so to increase their stability. And in this sense, we have studied the magnetism of dysprosium metal-organic networks on Cooper 111. The dysprosium atoms have been coordinated with these 2 molecular linkers, TDA and TPA. So we have investigated the structural properties using this low temperature STM and VT STM XPS systems. And the magnetism was studied in collaboration with our synchrotron by measurements of CHAS, XNLD, and XMCD. So to prepare the samples, first of all, the molecules were sublimated with the surface held at 50 degrees to promote the depronation of the molecules. And after that, the dysprosium were evaporated, and also with the surface heated. And with this, the molecules coordinated with the dysprosium atoms, forming this nearly square lattice. So here I have a STM image of the lattice and also an optimized DFT model. Also with the DFT calculations, we have determined the coordination symmetry of the dysprosium atom. So the dysprosium is coordinated in eightfold symmetry that is better described by a square antiprism, with the symmetry axis normal to the surface. And this is the structure for the dysprosium TDA network. For the TPA, it is very similar, again with a square lattice and with the dysprosium coordinated in a square antiprism symmetry, molecular crystal fields. Regarding the electronic properties, we have observed both experimentally by STS and theoretically by DFT calculations that when the molecules are coordinated, the LUMO state is displaced to higher energies. So here in this graphic in purple, there is the LUMO resonance for non-coordinated molecules, and in red for coordinated molecules. Also by DFT, we have this here. It have been that observed that the bonding has a ionic nature as expected for lanthanide atoms. However, in the STS spectra of dysprosium centers, we also have observed a resonance at energies near the energies of the LUMO state, which indicates that even if the bonding is majoritary ionic, it also has a covalent component. For the synchrotron experiments, besides all of the two networks, we also have prepared a sample consistent of dysprosium clusters. So here I have the XNLD spectra of the three samples. All then have anisotrope for F orbitals, with the networks being more anisotropic than the clusters. To determine the anisotropy orientation of the orbitals, we have compared these spectras with results found on literature for dysprosium double-deckers. The double-deckers are molecules where the dysprosium is subject to the same molecular crystal field symmetry in our networks, with a square antiprism symmetry. But surprisingly, our spectra are inverted when compared to the double-decker. So it is indicated that in the net TDA and TPA networks, the symmetry axis of the orbitals is in plane to the surface, even if the symmetry of the molecular crystal field is out of plane. Now here the XMCD. All the samples have an in-plane magnetic anisotropy, again with the networks being more anisotropic than the clusters. We have compared this spectra with XMCD spectra for dysprosium single-standing atoms, and the dysprosium atoms have a almost isotropic spectra with a very small out-of-plane anisotropy, in opposition to the in-plane anisotropy that we have observed in our networks. Comparing again with the double-deckers have out-of-plane anisotropy, which is the expected considering the symmetry of the system. And even if our networks have the same symmetry, in our case, the magnetic anisotropy is not following this symmetry. So the explanation for this is not trivial. Here I have three systems that all the three systems have the same molecular crystal field symmetry, the square and prism, but only the first one, the double deckers, have out of plane magnetic anisotropy. In the second system, that is a dysprosium salt, the anisotropy is lying nearly in plane. It is explained by apical coordination with a water molecule. This apical coordination does not change the molecular crystal field, but it unlinks the magnetic anisotropy to the symmetry of the crystal field. And in this case, the magnetic anisotropy orientation is changed to nearly in plane. In the TDA and TPA networks, the in-plane magnetic anisotropy is explained by the interaction with the substrate. So in this case, the substrate plays a role of apical coordination that is similar to the water molecule in the case of this dysprosium salt. Again, unlinking the magnetic anisotropy orientation to the symmetry of the molecular crystal field. So we have an effective crystal field that's composed by both the molecular crystal field and the effect of that surface. And in this case, the magnetic anisotropy is in plane. We have calculated the magnetic moments by some rules. In this table, there are the values of the orbital spin and total magnetic moments and their respective anisotropies. The anisotropies were defined as the difference between in-plane and out-of-plane magnetic moments. The most important values here are the last row, the total magnetic moment anisotropy. And for comparison, I have here the values of magnetic moments for single standing dysprosium atoms. When comparing the moments for normal and grazing incidence, the values are very close, and there is a small out-of-plane moment anisotropy. While in our networks, we have observed a strong in-plane moment anisotropy. So this indicated that it's possible to tune the magnetic anisotropy by metal-organic coordination. In summer, we have found out that the magnetism of lanthanide systems on surface can be drastically affected by small structural changes due to molecular coordination and by interaction with the surface. And that it's possible to tailor the magnetic anisotropy of lanthanide elements on surface by coordinative metal-organic protocols. To finish, I want to acknowledge to all the people involved in this work from IDEA, ICM2, ALBA, and ICMM, and thank you for your attention.
Thank you very much, Sofia, for this nice talk, and also, once again, for keeping in time. So it's time for questions now. I see that everyone is very shy. It's a Monday morning, but come on. So I have a question myself. Well, there's one from the audience, so I will give preference to this. Fernando Bartolome is saying, a nice talk. How do you prepare the system? Do you sheet the surface with diatoms or do you evaporate?
I first sublimated the molecules with the sample heated at 50 degrees. And after that, with the surface still heated, the dispersal atoms are evaporated. That?
Hopefully, yes. Maybe if he wants to ask, extend the question. Okay, another question from Juan Moreno Lopez. He's thanking you for the talk, and he's asking, what's the deposition temperature of the TPA molecules?
Oof, I don't remember exactly the number. I would need to check it. I'm not sure. Sorry.
Okay. Is there any other question? I wanted to ask the measurement, the XMCD and the MLD, when you measure the magnetism of the diatoms. These molecular networks are on a copper surface. So how do you know there is no magnetism coming from the surface?
From the substrate.
Yeah.
Oh, I don't. I mean, here. I think that the copper. I have subtracted the background that came from the copper substrate. I have a slide for this here. Here. So this is the signal, and the raw signal, and the background was subtracted. But for the way the experiments are done, it's possible to also measure the XMCD and directly from the raw data.
Yeah.
So there's no contribution from the substrate to the XMCD spectrum.
Okay, thank you. If there is any other question, and if not, we will thank Sofia again for her talk, and we'll welcome the next speaker. Thank you, Sofia.
Thanks.
The next speaker is Leire Hernandez Lopez.
Hello.
Hi. So, if you can share your screen, please, and then we can get going.
Okay, can you see it?
Yeah, perfectly. So Leire Hernandez Lopez is coming from the ICMA at the University of Zaragoza, right? Is that correct? She will be talking about iron nanodots on metal organic networks. So please go ahead. Thanks.
Okay, thank you for the presentation. These 4 images here represent the outline that I'm going to follow during my talk. I will start by talking about the system that results from the evaporation of iron atoms on a copper 111 surface. Then I will continue describing the formation of a metal organic network and how we use this metal organic network to nanostructure iron. And finally, I will talk about the magnetic properties of these iron structures. So we start with a copper 111 surface as substrate under ultra-high vacuum conditions. So when we evaporate iron atoms on this copper surface, they get in contact with the substrate and get hybridized and start to gain a lot of mobility and self-assemble, forming these triangular islands of 2 atomic heights, usually 2 or 3. This is how we observe with the STM these triangular islands. As you can see, there are these type of islands have 2 atomic heights and this other have 3 atomic heights. This is a system that has been widely studied, but what we wanted to do was to nanostructure these islands into smaller dots. So there are other examples in the literature where iron is nanostructured with copper surfaces. In this work here, they used copper surface with a high density of steps. When iron atoms are evaporated on copper surface on flat surfaces, the iron atoms self-assemble into triangular islands. But when they find atomic step, they self-assemble, decorating this step like following its shape. So in this case, in a surface with a high density of steps, the predominant structure are the stripes. So in this work here, they observed that for those directions with higher density or higher number of broken bonds, the orbital magnetic moment was enhanced. In this other work here, they stabilized single atoms and very small clusters of 2, 3, 4 iron atoms. on a copper surface, and they do it by keeping the substrate at 4 Kelvin during the evaporation. So they observe a similar behavior for the smallest particles, which is the single atoms. The orbital moment is increased also. The only problem with this system is that it is not stable at room temperature. So what we wanted to do was to nanostructure these triangular islands into smaller dots by reducing the diffusivity of the substrate, of the atoms in the substrate. And we wanted to get the structures to be stable at room temperature. So what we thought to do was to introduce between the substrate and the evaporation, to introduce a monolayer that gets to reduce this diffusivity of the iron atoms when they get in contact to the surface. So the kind of monolayer we decided to use was a metal organic network, because metal organic bonds are strong but are weak enough to allow the bond formation and bond breaking, which is necessary to form structures with a very low quantity of defects. So for our metal organic network, this is the molecular precursor we were using. This is dicyanoanthracene, or DCA, and consists of an anthracene backbone and 2 cyano groups. This molecular network is simply formed by evaporating these molecules on the copper substrate at room temperature. So as we evaporate the molecules, they self-assemble with copper atoms provided by the substrate, forming the network. And this is how we see the network with the SDM. So the good thing about this network is that it is like a carpet. It is completely covering all the surface with a very low quantity of defects and with a single domain. And we could check it both by STM and by low energy electron diffraction. This is the usual pattern we obtain with this network. It has been measured at room temperature and at 25 electron volts. The molecular network forms an 8x8 with respect to the unit cell of the copper substrate, whose first order spots would be located here. And the fact that the 00 spot, which is this one, is almost as bright as the first order spots of the network makes us an idea of the good quality of the network. So this is the layer we formed on the copper substrate, and then we wanted to evaporate the iron atoms on it. In fact, we expected that the iron clusters, the nanostructured iron clusters, would be formed inside the pores or the nanocavities that leave the network, and that we would have an ordered array of clusters. But we evaporated the iron atoms, and this is what it happened. We did not get to introduce the iron atoms into the cavities, but the iron was nanostructured. These two images here have the same dimensions, and both samples have been prepared with the same quantity of iron. The only difference is that in this case, we first formed the metal organic network. So we are not getting an ordered array of nanoclusters, but we are getting to nanostructure the iron. There is one more way we could reduce the diffusivity of these iron atoms in the substrate, and it was by keeping the substrate at low temperature at around 100 Kelvin during the iron evaporation. And this is what we did, and we got a bit smaller nanoclusters and more regular. It is important to note here that although the deposition was performed with the substrate at low temperature, we then let the sample warm up because we wanted the structures to be stable at room temperature. So to have more accurate information about the morphology, the sizes of these particles, we performed a statistical study with several STM images of each type of sample. And we, due to the nature of the STM images, we studied separately the heights of the clusters and the projected area. So in the heights study, we obtained, for this case, we already knew from the literature that these islands have 2 or 3 atomic heights. And for the case of the dots formed on metal organic networks, they have almost all the clusters are between 1 and 2 atomic heights. In the case of the areas study, we obtained some more interesting results. For the case of the triangular islands, this is the area distribution we obtained. As you can see, this is a very wide distribution, and at 200 square nanometers, we still have islands. And this is the area distribution for the case when we introduce the metal organic network. As you can see, by introducing this layer, the distribution changes a lot. And to observe better this area, we need to use another scale. And like this, we can see that most of the clusters have areas between 1 and 10 square nanometers. However, as I told you before, reducing the substrate temperature during deposition, we obtain smaller nanodots that have this distribution, and all the clusters are between 1 and 8 square nanometers. By fitting this distribution with log normal curves, we could obtain a mean area of each sample. And this is what we obtained for the case of the deposition on the metal organic network. At room temperature, we obtained a mean area of 6.23 square nanometers. And for the case of the low temperature evaporation, 2.59 square nanometers. Both samples were prepared with the same iron quantity that we have labeled in monolayer units as 0.10 monolayers. We repeated this experiment with a half of this quantity, which we labeled as 0.5 monolayers, and observed that for the same preparation we have half of the iron quantity. We reduced also the mean area, and we again observed that by reducing the temperature, we obtain smaller particles. So to summarize up to now, we have a metal organic network that allows us to evaporate iron atoms into small clusters, and then we have two different parameters to change that allow us to have a certain control on the iron clusters. One is the iron coverage or iron quantity, and the other one is the substrate temperature during deposition. So once we have the samples morphologically characterized, we go to the magnetic properties. For measuring the magnetic properties, we went to a synchrotron facility to ESRF and measure X-ray absorption spectroscopy and X-ray magnetic circular dichroism in the L213 eddies of iron. We measured this for the three types of samples and for two different iron quantities or iron coverages that I have just explained. So with the spectral result and the help of the SAM rules, we could get an estimation of the orbital and spin effective moments. Also with XMCD, we measured hysteresis cycles, and we observed that for the smallest particles, the cycles are more open, so we are enhancing the coercive field. So to summarize the magnetic properties in this plot here, we are plotting the orbital moment and the coercive field as a function of the area, the mean area of the particles. This dot line here corresponds to the orbital moment of the iron and copper triangular islands, the large ones, and this dashed line corresponds to the coercive field of the same islands. This spot here, which comes to this reference here, is the orbital moment of a single iron atom stabilized on copper, and this is the data of our particles. As you can see, it fits well between both limits, and both of the parameters follow the same tendency. They are enhanced that particle size is reduced. This is due to the high number of edge atoms with respect to the total number of atoms in clusters. So to conclude, we have formed a metal organic network. This metal organic network allows us to nanostructure iron. We have two different parameters to control the size of these nanoclusters, that are the substrate deposition, the substrate temperature during deposition, and the iron quantity or iron coverage. And finally, we have observed that both the coercive field and the orbital moment increase as particle size is decreased. So finally, I would like to acknowledge all the people involved in this work and founding, and thank you for your attention.
Okay, thank you very much, Leila, for this very nice and clear talk. And so the field is now open for questions. So we have a question from David Ecija, who's thank you for the nice talk, and also asking, have you tried to deposit minute atoms of iron at low temperatures?
Lower, yes.
Like very small, like tiny amounts of iron atoms. I think.
Yes, but in fact, this is the image in the index. This is like the lower quantity of iron we have deposited, and we observe more or less the same.
Mm-hmm. Okay. Any other question? I have a question myself. When you measure the magnetic properties, is there any possibility that some of the magnetism is coming from the monolayer? Which, by the way, when you deposit the iron atoms, might be somehow modified, no? How do you check the integrity of this molecular layer? Or is anyway?
The XMCD is an element selective technique, so it could be like inducing some magnetism, but I think I don't know if it's since it is an element selective technique. You know that the magnetism you are measuring comes from the iron.
And about the monolayer, because when you deposit the iron atoms, how do you know that your monolayer is staying as it was originally? Or is there any indication, how can this monolayer be modified? Or
Yeah, in fact, it is broken. In this image here, you can see it. We usually, when we form the network, it is quite perfect, but when we evaporate iron atoms, it gets destroyed a little bit. So, it is distorted, but I don't think it influences the magnetism.
Okay, thank you very much. We have a question from Juan Moreno Lopez, and he's asking, usually, he said, well, he's saying when metals are sublimated, high vacuum is applied, which ultraviolet is applied, which implies accelerating of the metal atoms. Do you think the sample is getting bombardment by the iron atoms? And then he says you already replied. That's probably similar to what I asked about the integrity of the molecular layer.
We have tried to, maybe this is true, but we have tried with different fluxes, so to deposit very fast, to deposit very slowly, and we always get more or less the same. So maybe this is something it affects, but I think we are getting always the network destroyed. I think they are the iron atoms, like when they move to self-assemble, that are destroying the network.
Okay, we have another question from David Ecija, and he's asking, have you measured the XAS of a nitrogen peak at the synchrotron?
Have you measured the
XAS?
Yes, of? Sorry, of?
A nitrogen peak.
No.
X-ray absorption spectroscopy.
No, we haven't measured it.
Okay, so if there are no more questions, we'll thank Leila again and move on Thank you very much. Gracias, Leire. We'll move to the last question. Oh, sorry, to the last talk of the session. So please, Leonid Chernoshatomsky, if you can share your presentation.
Yeah, thank you for your invitation in this very marvelous conference.
You're very welcome. Thanks for joining us. And you are coming from the Institute of Biochemical Physics in Moscow, and you will be talking about moire diamines based on near 30-degree twisted big graphenes. So please go ahead. Thank you very much.
Вот это мне мешает. Yeah. The name of my talk about moire diamines based on near 30-degree twisted big graphene. Couple words about history of the big graphene. Two-dimensional structure called last 15 years. Anomalous attention on research have been added by new member of Diamant. Name it as similar and analog names graphene, graphene. This all aspect 3 carbon dielectric materials was predicted ab initio our group in 2008. This is picture. We see diamond structure formed from AB layered big graphene, and this when it formed by hydrogen, when hydrogen atoms settle from both two sides and innovate adhesive on carbon atom located over each other neighbor layer, looks like here. And earlier derivative diamond materials is as one surface only hydroxyl group covered multi-graphene was obtained and named as diamanol. This is not only it can be organized diamond, also when big graphene covered fluorine atoms. That is, we see fluorine diamond revealed in group rotary roof. This is experimental data, pristine and fluoride graphene, and the very good picture and simulation of this structure, and this simulation looks like this picture, and they obtained the very tip-top pictures, experiments and theoretical pictures. And it's possible also organize diamonds based on multi-layer graphene, looks like here, that 2 layers or maybe 3 layers. And fluoride diamond looks like here, it's with a different kind of orientation. And if the fluorine diamond based on Billy graphene have a little higher energy gap, about 4 eV. You can see number of layers, and this is energy gap, different kind diamond with changing of number of layers. We predicted in this paper. And also in the last year, a group of Piazza obtained low temperature pressless transformation bigraphene, and they obtained crystalline carbon thin films. Looks like here, area about 140 micrometer to continuous CN bonding, and this is picture of image Raman spectra. This is very the same which we predicted in this paper. We computed Raman spectra of diamond films, a different graphene and compared with graphene. Synthesis and electronic structure characterization of diamond was obtained by a group Feng He. They used and demonstrate multi-layer diamond and successfully synthesized by compression about a few EPA under decompression. In addition, they find synthesized at a high pressure and high temperature, and it could be recovered back to ambient condition. And we proposed new structures using twisted bigraphene near angles 30 degrees. This is bigraphene with angle 29 and in unit cells of this bigraphene have 3,388 carbon atoms. This is a very large unit cells, and the difference we observed very high difference hydrogenation and fluorization features. It's possible to cover this graphene, twisted graphene, periodical by pairs of hydrogen atom. Looks like this complex you can see on this picture. HCCH complex, similar to cover both types of graphene in observed earlier. And this is type very contrasted in contrast of ordinary diamonds, where its surface is covered with alternating atoms. Here we see the experimental, very nice experiment where fluorine atoms organized the lattice with double addition of fluorine atoms. Looks like both type of structure. Such type we considered earlier and obtained that very high energetic stable form. Another, we check three types of twisted bigraphene with three different angles. For example, in this picture we see the diamond 21.8 angles. We can see this in this paper, in this place. We can see the cross section of complex, and looks like more brightly picture this, and this is diamond from the side, and this is this picture compares with ordinary diamonds, and another picture is diamonds with angle 27.8 degrees. You can see it's a distribution, not the same. This distribution of bonds, very different. Bonds have different direction. It's not perpendicular to normal of surface. Bonds. Band gaps. In this picture, we see bond gaps, diamonds, and Phtor diamonds, and this is very good. It's a very good features. Spectra have different, very high peaks of density of states. It's very good to use for optoelectronics and optics. We check also Raman in infrared spectra, these diamonds in comparisons with ordinary diamonds. We can see here red AA diamonds, black AB diamonds. This is a picture of 21.8 diamonds distribution of vibration. On this picture, we see Raman in here spectra of diamonds, 4 diamonds, in comparison with the usual ordinary diamonds. And you can see in this picture, we can see very vibration in the plane of films. It's a difference from the Raman spectra distribution of vibration in ordinary AB diamond. Presence of active unknown modes polarizes parallel these films. That's why we derive 2 main features of twisted diamond: wide gap and frequency shifts, and phonon modes with parallel polarization. And also we check another example, 27.8 degrees rotating angle of B graphene, which can we use for formation of 4 diamonds. And this we can see unit cell, and also this is red balls is a covalent bonds. This is place contain complex FCCF complexes. And also we can see non-parallel to normal directions of different bonds. We computed band structures and density state, and observed also very good gap of these structures for diamond 4.5, for fluorine diamond 4.5, and then we considered atomic model as twisted with large angle close to 30 degrees, 29.4. And also we observed very high direct band, about 5.8 EV. This band is larger than ordinarily diamonds, about 3 EV. That's why our Moir diamonds looks like 2-dimensional amorphous diamond films, because not parallel bonds, CC bonds. My summary. Summary. Последний. We calculated band gap of this diamond, and observed very high value. It's interesting for some wide gap dielectric devices, broad density of state peaks distribution allows to hope to good using in ultra-wide band gaps optoelectronics nano devices, and also it's a controllable, reproducible way of preparation method of these more diamonds should be the same as preparation of ordinary diamonds from bigraphene by its hydrogenation and fluorination. This fluorination in the hydrogenation system will be enabled to creation of new optical and electronic elements using this new two-dimensional wideband materials. Diamond materials constitute new synthetic carbon nanoforms after fluorines, non-diamonds, and so in graphite. This opens the door of new research in multiple areas for development of new potential implications. Thank you for your attention.
Okay, thank you very much, Leonid, for your talk. And now we'll be ready to go for the question session or for the question round. And Dr. Ochoa is asking, he's asking that in your calculations, you always consider perfect layers. Have you tried the effect that isolated defects would have in the local electronic properties, for example, in the band gaps? What happens if you put defects in your layer?
In a layer, yeah. When I put defects, it must be organized some levels in the band gap. Some papers now were prepared and they used the model with different defects. Yeah, and that's why in the band gap, in the band gap, it can be organized some levels. It depends on the type of atoms. It can be organized. It looks like the similar semiconductor. You can organize P semiconductor or N semiconductor.
Yeah, sure. Okay, I don't know. Maybe I missed it, but I guess all these calculations are done at DFT level. Is that right?
Yes, all calculation was prepared by DFT method Siesta program. Yeah.
These unit cells are huge, right? This is very
yeah, we use the more simple because it's this is very high unit cell contains 30,000. 388. This is.
So you consider a simplified unit cell, a smaller one?
Smaller. This is more smaller this.
Okay, so this is
Yeah, you can see this is more smaller, but not so perpendicular bonds. This is not so perpendicular complex.
Okay, we have another question from Daniel, and he's asking, have you looked into the localization of electrons and or Hall states near the band edges? Are these states localized in different regions of the moire, or are they delocalized?
This is you means это what the example?
Sorry, say it again.
In this, where localized all this high density state, yeah? There are many types. In this case, there are more density of electrons localized near these rings. Looks like here. Here.
This okay.
Is here. In the corner of unit cell, you can see. Usually here.
Okay. So, so the electrons, these localized states in the density of states correspond to this.
Looks like here,
okay,
in this place. Looks like here in this place.
Okay.
It's a ring, near rings. Near these rings.
Okay.
And small connection between electrons from this to these rings.
Okay, I think that answers Daniel's question. Is there any other last question for this talk and for this Monday session? If that's not the case, then we'll thank Leonid again for his contribution. And then, as asked by the organizers, I would now please ask you to turn on your camera so we can take a group photo. And well, have a little